Okay, so what I will discuss is about how to interpret the absorbance spectra. I've already shared this with you during the Hive lab. We are using the nanoshell as a new LFA reporter, and the reason that we are interested in it in the LFA assay is that it gives a stronger extinction. Okay, that means it has a higher contrast against the membrane. So that's why we use it in LFA. And this property is actually related to the plasmonic property. So I explained the plasmonic property last time. So here just refresh a little bit. And also the way that we using it to check whether our antibody conjugation is successful or not is also because of their plasmonic property, but not in the same way as they're doing as a reporting LFA, and more based on their the sensitivity to the refractive index, okay, and changing around the golden nanoparticles. So I talked about there are two types of surface plasmon resonance. One is the propagation mode, okay, on mainly the the metal film, okay, and in the plasmonic property of a golden nanoparticle or golden nanoshell is related to its localized surface plasmon resonance. So what does that mean is that when the light is excite the nanoparticle, there will be free electrons generated, and this free electrons is called surface plasmon, okay? And this surface plasmon is very sensitive to any material that's surrounding the surface, okay? So that means, for example, for golden nanoparticles, if there are material attached to it, there were changing is like the resonance of this surface plasma, and that's in absorbance measurement will be reflected as a small red shift, okay, of the spectrum. So I think that's that is what we observe with our golden nanoparticles. I think that's a bit obvious, and but the golden nanoshell is probably not that obvious, and I will explain a little bit more. Okay, so the golden nanoshell, what is doing is that first it has a silica core, okay, and then it grow a gold coating around the silica core. Okay, and golden nanoparticle, it only have the media and the gold interface, but the golden nanoshell, because it has the silica shell and the gold coating, it actually has both the media and the gold interface, as well as the gold and the silica interface. Okay, so it has two interfaces. So it makes things a little bit more complicated. So here you can see that this is a study from, so you can check this review paper. So it said that when it actually coating the silica core with a shell, you see that when it's increasing the layer of the gold, the peak actually has a blue shift, okay? And also within the increase of the thickness of the gold layer, it's starting to have this another side peak. This is another order, okay, of the resonance. That is because of the I think the interface between the gold and also the silica, okay? And the reason that why the golden nanoshell is interesting is that by controlling both the size of the core and also the layer of the gold, it actually can control where this big peak located. You see, it can come in a very broad range of the spectrum. So that makes it very easy to control. Okay, so I actually plotted a little bit of one of one group's data. Okay, so I just want to mention when you plot it, instead of just plotting the X as a wavelength and the Y as absorbance, it's better if you plot it in a normalized absorbance spectra. Okay, so when you not plotting as a normalized spectra, you will see a little bit drop, okay, in the intensity of the nanoparticle. I believe that's what all of you observed, and the dropping of the peak may be related to like the loss of nanoparticle. Okay, so first, the dilution we're using before and after the conjugation is different. So the after conjugation is a little bit more diluted, okay, than before conjugation. And second, you will lose some particle when you remove the supernatant. So that's why you see a little bit dropping in the spectrum, but that can't be interpreted as like my conjugation is successful actually. So if you see a little bit broad of the peak, so the broaden may be related to some of the aggregation. So that's how you can interpret the nanoparticle spectrum. So if you plot it by a normalized spectra, so how I do normalize is that, so I first find the maximum absorbance value in the whole data set, and then I divide each absorbance data by this maximum absorbance value. And then I can plot it, you see that both the curve located in from 0 to 1. Okay, so in this case you can have a bit better comparison, okay, before and after the conjugation. So for gold nanoparticle is a bit obvious, so you can see a slight red shift of the gold nanoparticle before and after the conjugation. But the gold nanoshell is a bit less obvious, so there are some reasons. So first, let's have a look. So the nanoshell has two peak. Okay, it have more peak than the nanoparticle, and this is associated with what I said just now, both the interface between the gold and the media, okay, and then the gold and the silica interface. So these two like interface produce like another peak, okay, of the nanoshell. And okay, so the peak that the nanoshell appear at 800, that is more like towards longer wavelengths, is due to like the size is bigger than the nanoparticle, okay, and also you can see it's actually broader than the nanoparticle. That's also have some reason. One reason is mainly because, okay, when they produce this nanoshell, it's not very like monodispersed. So the size is not monodispersed. So all different sizes of the nanoshell may produce a broader peak. And also because the way it grows, the gold will introduce a bit rougher surface. So the rougher surface will cause like more light scattering that can broaden the peak as well. Okay, so that's why you observe two peak, and also the peak in nanoshell is broader than the nanoparticle. Okay, and as I mentioned just now, the nanoshell you see is a bit hard to see the red shift, and that's also due to some reason. So first reason is because you see this peak is very broad, so that makes it a bit harder to actually observe very small red shift. Okay, so that means, so when we do like the optical sensing, there is a thing called like the high Q factor. That means we need to produce very narrow peak so that we can observe very slight change. But here for the nanoshell, because the peak is too broad, so it's very hard to observe. Okay, and also another possible reason is that what I think is that maybe this product it is the ratio between the core and the core size and the shell thickness is actually not optimized. for refractive index sensing, because these products is made for using as the lateral flow assay. Okay, it has to be bright, and that doesn't mean that it's very sensitive to refractive index change. So that is maybe another reason. And the third reason is actually maybe our like the antibody conjugation is not very successful. That is also possible. So what you can see is that in the afternoon, when you doing the lateral flow assay, if you see no lines of, say, the control lines, that may be due to like our conjugation is not as successful as the nanoparticle. So we have to see your lateral flow assay result and then to interpret it this absorbance, because right now we don't have other ways to like check whether the antibody conjugation is successful or not. Okay, and the last thing I listed here is that when we use it to work as a refractive index sensing, the good way to actually check the sensitivity is, instead of doing the antibody conjugation, if we can put the nanoparticle in a different solution that with different refractive index change, that will be making more obvious to see whether this peak can redshift when the refractive index change. Okay, so that is the very basic thing that we can do in the future if we want to see whether this nanoshell responds to the refractive index in the environment. And I listed here one paper that is a good paper that actually used the nanoshell and is like surface plasma resonance sensing related to refractive index change. So if you are interested in this topic, you can check this paper and also other paper that related to more series and like the optical properties of this nanoshell. Okay, so I think that's basically it.